Hot damn. Okay, let's go on. It actually proved this. And I'm going to erase this just in case we need the room. But I hope we know what that means. I can write down again if I want. Proof. And I'll say, start off, since we're not doing a direct proof, you always tell your reader what you're doing. What we're doing here is proof by contrapositive. Proof by contrapositive. And so you can even note, if you want, you don't have to say this, but you can. So we're trying to show that for all P and primes and for all A, the natural numbers, for all B, the natural numbers, P divides AB implies P divides A or P divides B. That's more for you guys. Just let us know what we're doing. Because this does in fact equal, this predicate right here is equivalent to P divides AB implies P divides A, P divides B. We talked about that already? Cool. So now we can just do a normal direct proof. We do a direct proof trying to prove the contrapositive instead of the original statement. So now it's kind of like we know. Let's go ahead and let P be an arbitrary but particular prime number, and A and B be arbitrary but particular in natural numbers. So that's the domain. We're saying these things are in the domain. Now assume, we're going to assume the hypothesis. But since we're not proof by contradiction, assume the hypothesis of the contradiction. So assume P divides AB. And this is the whole reason why contradiction is beautiful, because this is our foothold. This is exactly what we want. I hope you guys understand what footholds mean. If not, start climbing. It's fun. So assume P divides AB. Then by definition, there exists a K in Z such that PK equals AB. Now here's the part in the aside where we broke everything down as prime decomposition. So we know A is a prime decomposition because it's a natural number. We know B is a prime decomposition because it's a natural number. And we know P is prime, so it's its own prime decomposition. K, we know it's an integer, but by the definition it divides. We don't know yet it's a natural number. We haven't proven it's positive. It's going to turn out to be positive because, and we're going to prove it right now. So I'll say note, K equals AB over P. So since A, B, and P are positive, K, which equals AB over P, is positive. Thus, K is a positive integer. The same thing as being natural numbers. Little technical detail there. I almost left it out, but I thought, no, I'll get a good example and show all the details. So now we get to the fun part. Thus, since K is in N, by fundamental theorem of arithmetic, FTOA, I'm going to abbreviate it. Do you know why I abbreviate it that way? Because the first letter of F, fundamental theorem of, you guys get it. I once said somebody, I hope we all get this, but there exists the backwards E because it's E, like exists, all right? And for all is an upside down A because it's A, like for all. That's a really easy way to remember it. Like I wanted a person, like when I was taking this class back in the day, like whisper like, hey, I found out a way to memorize the there exists in the for all. Like the backwards E is E, like there exists. Upside down A is A, like for all. And I was like, yeah, that's why it's like that. Anyway, the point is, if you didn't know, now you know. So this is fundamental theorem of arithmetic. So since K is a natural number by the fundamental theorem of arithmetic, there exists, what do I call it? R1 through RT primes such that K equals R1 times R2 all the way out to times RT. It also says that it's going to be unique. So maybe you could even say there exist unique primes. But right now we just care that there exist primes. Further, since A and B are in N by the fundamental theorem of arithmetic, there exists, there exists, oh, I got this backwards. It'll all be fine. Q1 through QS primes, and there exists, what's a good letter? I don't want to use P again. Or A or B. C doesn't feel very prime. U, we'll use U. There exists U1 through UM primes such that A equals Q1 out to QS and B equals U1 multiplied by U2 multiplied by UN. So this is just A written as a product of primes, this is B written as a product of primes, this is K written as a product of primes. You have the letters different than the SI, but it's the same idea. Now here's where the billion part comes in. Thus, PK equals AB if and only if P times K is going to be R1 times R2 out to RT equals A, which is Q1 times Q2 out to QS times B, which is U1 times U2 out to UM by substitution. Now, note the left and right sides are both prime, or I'll say products of primes, i.e. Prime decompositions for pk, which equals AB. They're the same number. So these are both prime decompositions for the same number. Like we were saying before, by the fundamental theorem of arithmetic, prime decompositions are unique. Then, since prime decompositions are unique up to ordering by the fundamental theorem of arithmetic, since we know that, the left side, P to R1 has R2 all the way to RT, and the right side, Q1 out to QS times U1 out to UM must just be reorderings of each other. Oops. Does that make sense? That's the whole idea, right? We wrote the left side and the right side in two different ways, right? Because they're equal to each other, and because prime decompositions must be unique up to ordering, that means these guys must be reorderings of each other. Okay. I'm gonna erase the top part of this proof. Continued. No, this is not standard erasing proof and going back to the beginning. You should probably just write all your proofs on paper because I won't know what you erased. But other than that, copy me exactly. Yeah. So getting this proof, we know that these two are reorderings of each other. Thus, the prime P on the left side must be in R1 out to RS, no, sorry, Q1 out to QS, or U1 out to UM, right? It's gotta be one of these. Thus, P either equals, so thus P is either in or P is in U1 and UM, right? We know one of those is true, maybe both. Because nothing saying that both A and B can't be divisible by P. Let's do case one. P is in Q1 out to QM. Thus, P equals to QI for some I in the index. Wait, this should be S here, I'm sorry. Some I in the index. Then, Can someone remind me where these cubes come from? Like where were they originally defined? What does Q1 times 2Q all the way out to QS equal?
Is that not the Fatoa?
Oh, we have to use the fundamental arithmetic, but I'm saying, just I legitimately forget. Is this B or A?
Oh.
I think it's A.
It's A?
Yeah, I think so.
A equals Q1 out to QS. Or I'll say there's going to be some I minus 1 times QI times 2I plus 1 out to Q. Actually, I should write it like this. QI's in there somewhere out to QS, which equals Q1 times P all the way out to QS. I'm just saying P is a factor in there somewhere. Thus, since Q1 since all the Q's are primes, they are integers. So A is an integer multiple of P. It's going to be P times a bunch of integers. Thus P divides A. The technicalities here are a little complicated, but the point is, if P is in one of these, if P is one of the Q's, well, A is just the product of all the Q's. So that means P divides A. It's in there somewhere. P, yeah. I hope that makes sense. Case 2. I'll erase this now. Oh, we're over time, but it's the exact same thing. If P is in U1 out to UM, thus P equals UJ for some J in the index from 1 to M, then since B equals U1 times U2 out to UM, which equals U1, there's going to be a UJ in there somewhere, times UN, which equals U1 times P out to UM. B is an integer multiple of P. Thus, P divides B. Therefore, in either case, P divides A or P divides B as desired. Woo! That was long. That's way longer than any proof I'll ever ask you to do, and probably a little more complicated than any proof. Yeah, definitely more complicated than proof I'll tell you to do. But if you can understand that, you get it. You really get it. This is contradiction mixed with fundamental arithmetic, all combined. So Yeah, so the contradiction takeaway is that instead of proving P doesn't divide A and P doesn't divide B implies P does not divide AB, you prove the contradiction. P divides AB, then P divides A, or P divides B. This gave us the foothold we needed to get our hands on the math, start using our definitions and things to actually prove something. The rest of it is just playing around with the fundamental theorem of arithmetic, which I think is kind of obvious, but also kind of not. The whole thing to get around is that primes are the atoms of integers, and they can only be broken down into those atoms in a unique way. So you start to see things like this. Any questions? Well, we didn't get to the most beautiful theorem at all, math. That will have to wait till next time. But until then, it's Thursday, basically Friday. It's people's favorite day. Have a good weekend, everybody. Friday's basically a weekend. Have a great weekend. Yeah, that's all I'm going to say. Have a great Thursday night. Have fun on Red Assignment 7 if you haven't already done it already. I know you people don't procrastinate. Look at you. The cream of the crop here? No way. Okay, well, I'm going to stop sharing, stop recording, people. Thanks for the good class.
Thank you.
Thank
Welcome,
you.